Hello, everyone. Welcome to Fraunhofer CML's Maritime Innovation Updates. I wish you all have had a very good week. First of all, I would like to thank CML's press and media team for organizing this event. My name is Andy, and I'm the moderator of today. As usual, we will have a small presentation followed by a Q&A section. This presentation will be recorded, and therefore, please turn off your camera and microphone during the presentation. If you have any questions, feel free to use your hand symbol or speak directly at the end of the presentation. Thanks a lot. So the topic of the week is SeaClear 2.0, autonomous docking into moving platform for marine waste collection. I'm very happy to have my colleague, Cosmin Delaire, here to talk about it. Cosmin has a master's degree of mechatronics from the Technical University of Hamburg, and he is an expert in technologies related to maritime robotics and autonomous vehicles. I'm sure his deep and solid understanding in the maritime world is going to give us some really interesting insights. Cosmin, the stage is now yours.
Thank you very much, Andy, for the very nice introduction, and a warm welcome, everyone. Thank you for joining today. Today, we're going to talk, just like Andy said earlier, about autonomous platforms, specifically USVs or uncrewed surface vehicles, docking onto other moving platforms. In this specific use case, we're going to dock onto another USV. So, that being said, let's get started. The agenda for today is comprised of 5 points. We're going to dive into the introduction and in the problem statement, understand what is the actual problem we're trying to solve. Then shortly go through the methodology and check the results and the further developments of the current
Cosmin,
platform.
are you sharing your screen already?
I wasn't, sorry.
Yeah,
okay.
Now it's working, yeah.
Sorry, Okay, now I think everyone can see it. Okay, so let's start with the introduction. First of all, the idea of the docking of a USV onto another is being developed within the project SeaClear2. In this project, we have a couple of other systems, mostly surface and underwater vehicles that are working together towards a common goal, and that is detection, classification, and collection, ultimately, of marine litter. We are speaking here of marine litter pieces that range from anything from 50 kilograms to 125 kilograms, so not small pieces, just to be clear on this one. There are also other topics and points within this project, but due to time consideration, we will not talk about them. However, the important point I would like to stress here is the fact that a USV called Shuttle Tendered USV is being developed for the scope of collecting or depositing the collected waste from the main vehicle, from the SeaClear2, by means of an underwater grapple. So after the collection phase is being finished, the last step is to deposit the collected waste within the shuttle tender USV. Then this process can be repeated until the final payload is reached, and then the waste can be taken back to shore. Okay, what about the test sites? We have performed docking in 2 tests or demo sites, how we call them. One was in the Harburg Werfthafen, which is a relatively enclosed, behind a lock harbor within the Hamburg port. And the second one was in the Marseille, in a marina within Marseille, in the south of France. The platform that we have been using is called SeaDragon. We're going to see it in a second. But the problem statement is the following. This SeaDragon, this USV, needs to dock and create its path up to its final destination, which in this picture is this yellow and black rib-looking vessel. While creating its path, there are certain obstacles. Some of them we know a priori, such as the the margin of the waterways. This is something you can easily depict here by the black line, by the black polygon that's enclosing the area. But besides that, we will also have dynamic obstacles, or let's say uncharted obstacles, such as, for example, these other vessels that are being moored next to the ship, which of course for a human being it's easy to detect, but because the process needs to happen autonomously, there are some further steps incurred. Okay, so I was talking about the platform. The platform is called SeaDragon USV. It's a 5.5 by 2.1 twin azimuth propelled catamaran. It has a payload of approximately 450 kilograms. And it's for the current problem. We propose the following architecture, which involves 4 main states or 4 modes of operation. That is path following, that is going from A towards a very close proximity of the moving platform, then diving into or switching towards docking, which is a state in which the moving platform is precisely monitored so that we can dock stern to stern. And for this, we have, you can imagine, a space of maneuver, or let's say tolerance of approximately 20 to 30 centimeters. So that's the maximum we can afford left or right from the platform. Because of some obstacles consisting of some pontoons connected to the vessel. But those are just details. Once the docking has finished, we enter a so-called station keeping mode. This is a loose connection. We want to just keep our position while also making sure that the other vessel is not moving outwards from our rendezvous position, so that the litter can be safely deposited without having any incidents. Okay. So for just a bit of the control part, we have a line of sight control, which basically follows the next waypoints, so to say. But these are a discrete series of waypoints, which are significantly more than just a couple of GPS positions, because every segment is then discretized further on into smaller pieces. These are given by an A-star algorithm, which we're going to see in the next slide. And the idea is to minimize the lateral and the forward, or how we call it here, cross-track and along-track error, until we reach a certain radius of acceptance, in which and from that point onwards, we consider that that point is reached. Very classical approach from this point of view. We added on top an A-star planner, which essentially discretizes the sequence of between 2 given waypoints into multiple ones, taking in consideration several factors. And it essentially keeps the track of those little discrete intermediary waypoints while the ship is crossing them. Okay. Just a bit of comparison, so you get a feeling on that without using A-star, so just simply following a few, in this case, 4 waypoints, we obtain some root mean square error of 5.3 meters, while the error has decreased almost by half when using the A-star plan. So it's a bit more efficient to use it. That's the key point, and also decreases the sailing time to approximately 25%. That's just a minor thing to mention, but relatively a lot of added value when you consider longer tracks of a few kilometers or nautical miles. Okay, now let's dive into the results. So we're going to look a bit in the docking itself, in the path planning itself. So in this sequence, we have the shuttle tender USV in this video in Marseille, coming from the quay side and being located at approximately maybe 70 meters from the final position, which is the moving platform, as we called it, the SeaCat USV. The goal is here to reach the area behind the SeaCat within the next 30 meters and then switch into the docking mode. So from the perspective of sorry, I missed here. I have to play it like this. Okay, so as you can see here, the ship is approaching. It's trying to get in the stern behind the SeaCat, the platform to be docked on. And once it reaches the approximately 30 meters from it, it switches into docking mode, which involves a change of pose, of a 180 degrees rotation, because we want, again, to dock stern to stern. Now, we can do this because our ship, as mentioned earlier, is propelled with a twin azimuth drive. That means we can actually control the sway of the ship and have, let's say, less hydrodynamic sail sideways from the target, and we can compensate for these errors. Okay, now moving towards the docking. This is, of course, the last meters I skipped towards. And in this part, you see how the ship is actually slowly minimizing the errors within the last meters, braking constantly, adjusting a bit left and right, trying to get towards the sweet spot, which is the space between the two pontoons, or let's say the two hulls of the main ship. This is essentially the part where the station keeper begins from. And for this, we simply push lightly against the other ship. Not to be confused with dynamic positioning, because dynamic position is not a good idea in this case, because the ships might slightly drift a bit, and we do not want to set up a fixed position for that. This is a bit different. Maybe the naming itself can be changed, but the idea is this is a slight push against the moving platform. Of course, if we have a rotation of the moving platform, we will account for that and try to always go against it and not in the same with the same heading as before. Okay. Okay. Limitations. We encountered two main limitations. One is the minimal cost solutions. These are due to the fact that A-star always tries to minimize the path, whatever the reasons are. So whatever the most humanly friendly path would be. That translates into some paths being very close to the harbor or the quay walls or right next to the margins of the waterways, which is essentially dangerous. That means that we have to account for this and penalize the paths so that we keep the ship towards, let's say, in the middle of the waterway or on the right side of the water lane. The second part is the dynamic obstacles. This is the part I haven't touched in this presentation. I'm going to touch it a bit here in the future works. Essentially, we will not be able right now with this approach to detect any uncharted elements, such as, for example, you can see behind this or in front of the ship, this moving small USVs. These are the kind of targets that no chart includes or has them. So we need something to make sure we avoid collision with them. These are the dynamic obstacles. Okay, so for the first part, for the path planning, we're going to integrate Debian curves for smoother navigation and add in a so-called inflation layer for keeping the USV within the waterway. So as you can see the right-hand side picture, we would like to have to kind of limit the options so that we keep our USV within the middle of the canal in this case. This is trivial for a human being, but not that trivial for an unmanned system. Of course, this comes with a lot of background computation and actually trying to increase the costs of the solutions that are not within this range. The same applies for dynamic obstacles, the same principle of inflation layer adding for vessels that might cross our path. It's a similar idea. And lastly, as I mentioned, integration of a local path planner with dynamic LiDAR-based obstacle detection. As this is something we have been working on already. You see it on the right-hand side, how some of the marine traffic participants. So, in this example, we have 4 vessels, the one I presented in the beginning, moored next to a quay wall, that are being detected, and there's some kind of a bounding box that is covering them, so that we can compute our next desirable waypoint using this information and doing it online, like while sailing. Okay. That being said, I hope you enjoyed this presentation. If you have any other questions, feel free to reach out. I'm gladly to explain you the further concepts, the further ideas behind our unmanned or uncrewed system. There are, of course, many aspects I could not cover today, especially the control and navigation part. But should you have any questions, feel free to reach out. And with that being said, I hand over to Andy.
Thanks a lot.
If we have any questions or...
Yeah, thanks a lot for the informative lecture, Cosmin. Now we open the stage for the Q&A section, and you are all welcome to join the discussions. So I think we have time for around 2 to 3 questions.
Sure.
Anyone? So if not, I think I got a question from Leonard before the presentation. So he asked about how is the wind effect taken into account in the control system, because we see that you are doing in a relatively calm water, calm wind situation.
Yeah. Maybe I'll go back to this slide with the docking. So the wind itself, yeah, you can see it in the video. There's actually a calm water scenario. The wind situation in that specific day was always also relatively calm, I would say. So we had around 7 to 12 knots, maximum 12 knots, but at least 7 knots of wind speed. This is taken in consideration in the calculation in form of a compensation from the wind forces that are measured by the onboard wind sensor. So we have 2 degrees of freedom, one on the transverse on the transverse of the USV, and one on the side. So we can measure this forces, and give respective penalty, the corresponding penalty for this drift. It will not be possible without measuring the wind speed or the wind force, as this will account for noise or disturbances more likely. So we need to measure our disturbances so that we can compensate for them. But we do have the means for it. And I'm not saying this is 100% bulletproof. It's a mean of compensating, which is on site, because we cannot rely on forecasts. Forecasts are general, whereas we encounter different aspects of the wind, such as swirls or actually lower wind because of the quay walls or wharfs that are being around the harbor area. So it's more of a local problem. So we need a local measurement for the wind for the wind disturbances, wind generated disturbances.
Okay, thank you. One last question, anyone? Okay, if not, I will ask. So I don't know how difficult is this docking test. How does it compare to manual remote driven by human? How about after a few practices, can we handle it easily?
Interesting question. Actually, we tried it. So it's of course doable if the operator has experience, and but imagine yourself, probably some of the people here have driven some sort of drone. Imagine that you can actually turn left or right conventionally by having one of the side motors, one of the two motors spinning faster, so you can turn left or right. That's something humanly doable, but calculating what's a deflection of the thruster so that you achieve the exact behavior you would like is something that comes with experience, and it's for sure not as easy to do it for any kind of desirable position. Just to give an example, you might have from this position that we see here, we are slightly a bit towards the starboard of our vessel. So we would need to compensate more in the back in the port of it. So you have at least 4 to 5 combination of thrust plus thrust deflection, or rudder deflection that can be used for this. Now imagine having two. Most of the vehicles that we pleasure crafts are equipped with one rudder and one motor for steering, or let's say they are coupled. Imagine now having two independent ones, and how would you place them? I think it's doable if we couple them and just do it like classical rudder plus thruster combination for pleasure crafts. Still, this will require a lot of practice, and the most problematic part is drifting sideways while being in a close proximity, which is something really difficult to maneuver or to handle.
Okay, thanks a lot for the very detailed answer. So I think this marks the end of this week's MIU. We wish you all have a very nice weekend, and next week we will have cover the anniversary of the CML 15 year.
I think in 2 weeks from now, actually.
In 2 weeks,
in 2 weeks from now. Yeah.
Okay, looking forward to seeing you all again in the next MIU. Goodbye.
Cool. Thank you very much, everyone. Have a nice weekend. Bye-bye.